So last time we left at this stage. So we were discussing about some second phase of the heap sort. So here is the second phase beginning. So this is the exact max heap which we obtained in the last lecture. So now we will begin with from here. Okay, so what we do is we maintain a variable size which represents the current size of unsorted array. So initially size is equal to 8 because the whole array is unsorted. Okay, so what are the steps of our algorithm? This is our algorithm. Let us examine the steps of our algorithm, and then while practicing the steps we will make them clear. So first step is swap the A1 element with A size. That is, for now we need to swap the first element with the A size, that is A8th element. That is, we swap 20 and 5 to obtain this array. Then the next step is decrement size. Now 20 is originally the largest element, so we have taken the largest element to the end by doing this swapping. So 20 is in its correct position. Now the size of the unsorted array becomes just 7 from first element to the 7th element. So the second step is but obvious, that is decrement size, that is size minus minus, because A1, which was the maximum element, why it is maximum element? Because it is a property of max heap, has reached its correct destination, and hence array of size minus 1 elements is yet unsorted. Okay, so now what is the step 3? Now take A1 to the correct position so as to make that size minus 1 array a max heap again. Now we have got an unsorted array of size minus 1, that is size 7. In this array all these elements from 2 to 7 are at their correct positions, but this one element, first element, which we just inserted, has disturbed the balance of this max heap, because this is inserted in an arbitrary position 1. It doesn't deserve to be at this position. So what we do is we take it to its correct position. We swap 5 with greater of the 2 children and continue this as we go down the tree. Remember the pictorial representation. So 5 has 2 children named 13 and 12. So out of these, 13 is the larger children. So 13 deserves to become the root. 13 becomes the root, 5 comes here, and 12 remains at the right position, earlier position. Now 5 has 2 children, 10 and 6. 10 deserves to come at 5's position, so we swap. So 10 comes here, 5 comes there. Now 5 has only one child, that is 8, but no, it is not a child because the size of max heap is just 7 and 8 is out of range, so we don't consider this. So this 7 size max heap is ready. This is a perfectly valid max heap of size 7. You can verify by drawing it pictorially. Now we again begin with step 1, step 2, step 3. So we iterate this how many times? The number of elements, that is 8 times. So we again start with step 1. We swap 13 and 8. 13 is the largest element which goes to its correct position. So 13 and 20. These are both freezed here only. Now we don't have to deal with them. Now 8 comes here. Let's see who its children are. 8's children are 10 and 12. So we swap 8 with 12. 12 comes here. 10 and 8, 5, 6, 4, and 13, 20. So 8 and 4. Now there is no need of swapping because 8 is the parent, 4 is the child, which is perfectly valid. So this remaining array of size 6 is a perfectly valid max heap. Now we again follow these 3 steps of our algorithm. Okay, so we were somewhere here. Now we come here. So what we do is we swap first element with the sixth element. To get this, we decrease the size decremented, hence size is equal to 5 now. So these 3 elements are freezed, we don't have to deal with them anymore, and this is the remaining unsorted array. So we take 4 at its correct position, its two child are these. We swap it with the greater one, that is 10. Again 4's two child are these. We swap it with 6 comes here. Now it is a maximum heap of size 5. Now we again start with step 1. We swap a1 and a size, that is a1 and a5. 4 comes here, 10 comes here. Now we decrement size to freeze 10 here. Now the max heap size is just 4. The unsorted size array is just 4 in size, not a max heap, sorry. Now we see who 4's children are. 6 and 8. 8 is the bigger of the two children, so we swap 4 with 8. 8 comes here, and then 4's child is out of range, so we stop there. Now we swap a1 with a size, that is a1 with a4. 5 comes here, 8 comes here, and freezes there, and the size becomes 3 now. We see whose 5 children are 6 and 4. We swap 5 with 6. 6 comes here. 4's children is now out of range, so we stop. Now what we do is we swap 6 and 4. 6 freezes. 4 and 5 come here. So now the last steps. Okay, 4 and 5 come here. Okay, so 6 is freezed, 4 and 5 are there. We swap 4 with the greater of its child, that is we swap 4 with 5. 5 comes here, 4 come here. Again with swap, because a1 is swapped with a size according to the step 1 of our algorithm, and we get this. So 5 is freezed here. Now only one element is left, so we stop, because that element must be in correct position, and we have obtained the sorted array. You can verify by yourself. So as you can see, we have obtained the sorted array here only, but that we can see by our eyes, but the computer can't see this. Computer has to perform these 2 steps also. So you give an algorithm to computer and it can execute that only. So it performs these 2 steps also, and obviously in each step we are going down the tree which has height log n, and we are iterating this for each element, that is n times. So n into log n, number of times into height, n into log n. So n log n is the worst case complexity of heap sort. And thank you friends.